Using stoichiometry to calculate the equilibrium, but we're going to look at them in two different facets, and I'll give you practice problems as well to work on. So the first facet in this domain is going to be using perfect squares. And the second domain is going to be a little bit more rigorous in terms of workload. It's non-perfect squares, and we would have to use the formula, quadratic formula. We would have to use that when we tackle non-perfect square problems. Let's look at the first question. Well, we have our reactants over here and we have our products over here. Before we start putting them into the actual expression, let's start dealing with what we're used to dealing with, concentration. So we're obviously quite familiar with these brackets here that deal with concentration. So let's start off with just the reactants first. Our reactant here for the Br2 has 8.70 moles. And it's placed in 5 liters. This here is the amount of moles. We're trying to find concentration though, because we've always worked in concentration, and in our ice table a little bit later on in this video, it deals in concentration as well. Not all the time, but most of the time. So what we're going to do is, instead of just leaving it as moles, I'm actually going to be plugging it in and integrating it with the liters over here. Why am I going to be doing this? Because you should already know this formula here. C is equal to N over V. Our moles are on the top, volume is on the bottom. If we have both of these variables, we might as well put them together and put them and represent them as a concentration. Okay, so we're going to have our moles over here divided by our liters. In this case we have 5 liters, and we're just going to figure out our concentration now. So just use a calculator, you end up getting 1.74. So this would be 1.74 moles per liter. Okay, this is for Br2. Now let's do the same thing for Cl2. We're going to use the same formula. C is equal to N over V. So let's have chlorine over here, and same thing. This is the amount of moles of chlorine, also within a 5 liter container. So you just get the same answer. You just get 1.74 moles per liter. And next we're going to be dealing with bromine chloride over here. So let's write this out. So we have our bromine chloride. Obviously this becomes a little bit more tricky because we don't have this 8.70 moles of BrCl. It's only expressed for the reactant. Our product is not given in our little description here, so it's actually just going to be 0, okay, 0 moles per liter, until we start figuring out using an ice table. Now, what is this ice table? I'm just going to be putting I over here, C over here, and E over here. I stands for the initial, so we're going to be using concentration in this case. We're going to be putting our concentrations here in this row. C here stands for the change, so whether there's an increase or a decrease in the change within the mathematics of this expression. And then E is when we actually hit the equilibrium, because obviously that's what we're trying to find here, okay? So equilibrium here is just going to be adding a sum of these two together. Now it's important for us to always have an indicator, so maybe I'm just going to be putting it up here. I'm going to indicate that this is all going to be in moles per liter. In moles per liter. Okay, this means that any value that we put in here, like let's say 1.74, it's going to be referred to in moles per liter, not moles. Okay, it's a very important disclaimer that we should put. Okay, so let's put our first initial concentration. Again, we're dealing with moles per liter, so let's do that. We're going to have 1.74, so we're going to put that for 1.74, and then on the very top, so let's start off with our labeling on the very top over here. We're going to be dealing with our reactants first. Just go into that order, going from left to right. So let's start with, our Br2. Okay, so I'm going to be putting my Br2 all the way up here. And we're going to first figure out its concentration and then write it in this little chart. Okay, so in here it's going to be 1.74, and then we're going to move on to the next side. After that, the next reactant is Cl2, so I'll write that over here. What's that going to be? Also 1.74. I'm writing it as such. And then the very last one, of course, is going to be our bromine chloride. Let's write that out, BrCl. And of course, it's going to be 0. So we're just going to write 0 because obviously it hasn't been produced yet at equilibrium, right? They're still reacting. Eventually, it's going to start forming the BrCl, but initially at the beginning, there is none of bromine chloride. So let's continue to work downwards and we'll start dealing with our change, okay? So we have to start looking at our moles right now, okay? Our Br2 here, our coefficient, there is only 1, okay? This means that it has to be just 1x, okay? And we're going to be dealing with that variable here as x. How much did it increase or how much did it decrease? It's going to be in the form of x, but increase would mean that it has to be a positive symbol because you are gaining it, right? So positive obviously means gain. In this case, that's not happening, and Br2 is being consumed. It is being used up, which would be the opposite. It is not increasing, it is actually decreasing. So we have to put a negative symbol. So this will be negative x. Same thing for our Cl2. There's only 1 of it, right? We have a coefficient of 1, so it'll be 1x. It's going to be a negative as well because it is being used up to produce this bromine chloride. So I'm putting a negative x. Let's keep moving down. We have our BrCl here. Obviously, it is being created, it is being produced. So now we have +2, okay? Not +1 or -1, it is a +2, okay? Again, the reason why it's not a -2, it is because it is being produced, not being used up. So we have a positive symbol here. And then we're just going to be putting our variable for there. And then we're just going to add all of them up into this category of E. So we have 1.74 minus x, we have 1.74 minus x, and we have just 2x. Now, we have to put this all as an expression, okay? Let's put them all into an expression. Well, we first have our k, right? We have our k, and obviously we want this k to become KEQ, right? Once we figure out all of the pure substances being canceled out, and you know those states, if it's solid or or liquid, right? Those are obviously going to be a concentration that is constant, so they're not going to be expressed. Okay, in case you have no idea what I'm talking about, see the video link in the description about this, okay, for more detail. It is a precursor to this video. So now we're going to look at our K. We're going to assume that it has done what it needs to do in order to become not a temporary K, but a permanent KEQ, okay? So again, look at that video in the description to figure out how we get that KEQ. So let's assume we're on our way to get our KEQ at our equilibrium. We just have to put our products of concentrations on the top and obviously our reactants on the bottom. So we're going to have our 2x over here. This is obviously our product. This here is our product. These are our reactants. So I'm putting my 2x over here. Now, it's very important that we actually put a square on top as an exponent, okay? The reason why it might seem confusing, right, because there isn't any over here. Why would we do that? Why would we have to put a 2? The reason why is because of equilibrium delta G. This is not part of the video. It's going to take a very long time. I'm going to be creating a video talking about Gibbs free energy and delta H and its interaction with entropy. When I get to that video, you will have a better understanding as to why we have to put, if there's a 2 over here, we have to put it on top of there as well as an exponent. It's just because of this equilibrium dynamic of delta G. A delta G has to equal 0, and then once you do its little derivation, you'll figure out at the very end of the calculation that coefficient actually becomes an exponent at the very end. Why does the delta G have to equal 0? It's because when we get to an equilibrium, we assume that it is at a steady state. If it's at a steady state, we have to assume that the equilibrium of delta G has to have a local minimum, and that local minimum we assume it's going to equal 0, and do not forget to add it at the very top as an exponent, otherwise you're going to get the whole answer wrong. Okay, so just bear with me here until I get that video up and running to show you. Now we're going to get our 2x to the exponent of 2. We're going to get our denominator here, which would be our reactants. It would be 1.74 minus x and 1.74 minus x. So we're just going to write that here as such, and obviously multiply them together. And then from here, instead of adding our KEQ, we could actually just substitute it with our 28.8, because it says at 450 Kelvin, the KEQ is equal to 28.8. So this here will eventually become 28.8. You know what, let's bring this all the way up here so that it can be scaffolded to lay out a little bit easier. So again, our KEQ is 28.8, so let's write it out. And we have our 2x squared. And of course we have our 1.74 minus x. There are two of them, so if you multiply them together, technically it's actually just going to square. So we can simplify it in that fashion. So we can just put a square over there. Now it's going to be quite easy. We are dealing with perfect squares, like how I described in the title of this video. We're dealing with perfect squares and non-perfect squares. In this case we have a perfect square, because guess what? If you were to square root this, you could also square root this, and then you could also square root this one as well. So this should be quite simple. Just use a calculator here. The square root of 28.8 will give you a value of 5.3666. Okay, so let's write that out. 5.3666, and then of course our squared here is gone, so we're just going to be putting our 2x, and then on the very bottom here the squared is gone as well, so we just have 1.74 minus x. Look how clean this is turning out. Again, let's put this divided by 1, and then let's again cross multiply again. So our 2x is going to multiply by our 1, that'll just be 2x, and then this here needs to multiply by this. We'll use a subfoil method, obviously. So we have our 5.3666, and then you're just going to multiply by this 1.74 minus x in the brackets. What do you end up getting? Just use your calculator. This times this gives you 9.3378. Okay, so 9.3378, and then negative 5.3666x. Now what do we want to do? Of course we want to bring this x closer to that x, because we can eventually just put them together and then eventually find x quite easily. Right now it says negative 5.366. What's the opposite of that? You're just going to plus 5.3666. Obviously these cancel out. If you do this on the right side, you got to do it on the left side. So let's add that over here. So that's 5.3666. And then you end up just getting 7.3666. X is equal to 9.3378. Obviously we want to divide this so that we ended up just getting our x. Your x ends up becoming 1.27. Okay, if we were to round it into 2 decimal places. Now this value over here, we can insert it into here, insert it into here, and insert it into there. So what is going to be our concentration for Br2 after equilibrium? Because obviously this row here is dealing with equilibrium. So I'm just going to put moreover, our Br2 concentration is going to equal 1.74 minus this value. What do you end up getting? I end up getting 0.47. Okay, so this is 0.47 moles per liter. Okay, now we're going to do the same thing for our Cl2. Our Cl2 obviously should be the same. So we have this minus this. Obviously this is our x, so you get the same value, 0.47 moles per liter. And last but not least, we have our BrCl, and that's going to be 2 multiplied by the x, so 2 times 1.27 gives you 2.54 moles per liter. Is this what the question is asking? No, it's not. The question is asking what is the amount in moles of each reactant and each product, okay? Well, we found out the reactants and the products here, but they are in moles per liter. We want them in moles. So we obviously have to multiply by our 5 liters. Why do we do that? Because we don't want liters, right? We want only moles alone. How can we make this moles alone? Right now, it is not alone. It is being bothered by this divided liter. How do we get rid of this divided liter? The opposite is multiply by liters. So we're just going to do that. So this cancels out. Okay, but what liter are we dealing with? We're dealing with 5 liters. So we'll just put that over there. This cancels out, this cancels out. So you just get this times this. What do you end up getting? You end up getting 2.35. That's the answer, 2.35 moles, okay? For Cl2, it'll be the same deal, 2.35 moles. And for our BrCl, again, multiply by 5 liters as well, you end up getting 12.7. These are your answers. Very similar to the last question, but this time it's asking for, as you can see, concentration as opposed to just the moles. Okay, so this may seem a lot easier, okay, because we're just looking for concentration. But no, I'm giving you a warning, a little heads up here. This here will be a non-perfect square. I'll show you what this means, okay? But we still have to find out for both the reactants and the products. Let's write down our ice table, okay? So we got our I over here, we have our C over here, and we have our E over here. Let's put this all, again, disclaim that this is all in moles per liter, however way you want to make a disclaimer for your teacher so that they are aware. And then let's put our reactants and products at the very top over here. Okay, so we're going to be putting our reactants first. We have our CO over here. Let's write that out. Then we have our H2O over here. Then we have our H2 over here. And then lastly, we have our CO2. Now, we're going to have to put our initial concentrations. Well, we have our concentration quite easily just by looking at it at face value. Our carbon monoxide here is at 1.45 moles. But if we were to divide it, because our C is equal to N over V formula, right? It has to divide by volume here. Our volume is just 1. So it's just going to stay the same. So it'll just be 1.45 moles per liter. So let's write that out over here. We have 1.45. Again, this is all in moles per liter anyway. And then we're going to be dealing with our H2O. Our H2O, do we have it? Yep, our water vapor combined as well. And our water vapor here in moles is 2.22. Okay, so we're going to write that out as 2.22. In terms of our H2 and our CO2, we have no idea. It's not written in our description question. So we have to assume that it's just going to be 0, which would make sense because we haven't made it yet. Okay, these need to react in order to form those products. So we're going to start dealing with our changes, okay, an increase or decrease, and we're going to use X as our variable. What happened for our C? Well, it's going to be a negative, right? Sorry, our CO, it's going to be negative because it's being used up. Only one coefficient over there, so we'll just put 1x or x, and then we're going to do the same thing for our H2O. Okay, so our H2O, negative x or negative 1x as well. As we keep going, H2, it is being produced, so it is gaining, so we're going to putting a plus in terms of our value. For our variable, it is a 1x as well, and same thing for our CO2. Okay, it's going to be a plus x as well. You should have already realized at this point that this is all balanced. If it's not balanced, obviously you got to balance it out, but in our case, it's quite balanced well. Next, we're going to be looking at our equilibrium, okay, which means we're just going to add all of this up, so we end up just getting 1.45 minus x. We're going to do the same thing over here, 2.22 minus x, and then we're just going to be putting our plus x's over here. Now we're going to be putting them all into our expression. Now, our expression for a KQ is going to be 0.52, so I'll write that out. And then we got to write it out as our products on the top. We have our product over here, x. So we got another product over here, x. You got to multiply them. And then we're going to do the same thing down here. As I'm pretty sure you can kind of tell where the issue lies, where it's going to make our work a lot more difficult right now, right? Obviously, we have this reactant having completely different values here, okay? So yes, it is going to be a little bit more challenging, but it's okay. We're going to be putting our 1.45 minus x multiplied by our 2.22 minus x. And then, of course, they need to multiply with each other. Before we do that, we can obviously know what's going to happen with these two x's. Okay, these two x's, they're based on the exponent rule in mathematics, they would obviously add up. So this exponent of 1, this exponent of 1 would add up when this x values multiply. So you'll end up just getting 1x, because this is 1x here, 1x here. 1 times 1 is 1, so you'll end up just getting 1. But obviously its exponents will add up, so you'll be getting squares. So you'll be getting 1x squared. Write it out over here, so we have our x squared. And then our bottom denominator, that doesn't really change. We'll do that in the next sequence. Let's bring this all over up here, okay? So we'll start with our 0.52 is equal to our x squared all over the 1.45 minus x multiplied by our 2.22 minus x. Okay, we're going to now put them all together, but we have to start cross multiplying, okay? Before we start cross multiplying this way and this way, let's make it a little bit more simple by first calculating these two together, okay? We can't just do a combination of them and just putting a square on top, because they're obviously not the same. So we actually have to expand this, okay? So let's give this a try. So our 1.45 over here is going to be written out as such. And then this 1.45 needs to multiply this 2.22. So what do you end up getting for that? You're getting 3.219. Okay, so 3.219. This here multiplied by that one there, 1.45 minus x, gives you negative 1.45x. Do the same thing for this one. Negative x times 2.22. So it's obviously negative 2.22x. And then obviously this negative x, they multiply, you end up just getting plus x, and then obviously you get a squared over there. So we're going to be having to implement this in there, okay? So I'm just going to write this up here so I don't forget what it is. So we have 3.219 minus 1.45x minus 2.22x plus x squared, okay? 3.219 minus 1.45x minus 2.22x, and we have our x squared over there. At this point we could multiply them and cross multiply, so let's do that. So we ended up just getting our 0.52. We can put it in brackets just to make sure that it's going to remain clear throughout the whole sequence. So 1.52 minus this whole thing over here, okay? So we get 3.19 in the bracket, negative 1.45x. Actually, we can just, do this and this together, okay? So it's negative 1.45 minus 2.22. What do you end up getting? You end up getting negative 3.67, okay? So negative 3.67x, and then we have x squared, okay? Now, these are all multiplied. We got to do the same thing for the other side of the equal sign, x squared times 1, which will just be x squared. Now let's obviously expand subfoil method these ones together as well, and then we're going to slowly get to our conclusion. So we're just going to 1.52 multiply by that. What do you end up getting? You end up getting 1.6738, okay? So 1.673, actually technically 9, okay? And then we're going to do the same thing for this one, multiply that one. What do you end up getting? And I'm getting negative 1.9084, negative 1.9084x, and then obviously this times this gives you 0.52 x squared, okay? And this is all equal to x squared. Now let's start putting them all on the same side, because like I said in the beginning of this video, when we get to non-perfect squares, we have to put them in a format where we can use them in a quadratic formula. Let's actually bring this one over to this side, okay? You're probably thinking, why not just bring this one over here? It'll be a lot easier. The reason why that would be inconvenient, in just my opinion, is because then you have this one going on this side, which would become a negative, so you get 0.52 minus 1. That would give you a negative value for x squared. I always like to keep the beginning portion of that, our a value, to be a positive number. So I'd rather do the work and bring this all, this one too, all on the other side. That's what I would prefer to do. You don't have to do it that way. It is totally up to you. You will still get the correct answer by the end of this video. So I'm just going to bring this over here. Again, obviously this is 0.52. The opposite of that is negative 0.52. So I'll do that over here. If you do it on this side, you got to do it on that side as well. So, and I'm just getting this minus 0.52. So that would be 0.48. Okay, so I end up getting 0.48 x squared. So obviously we just got to bring this to the opposite side as well. So you end up just getting plus 1.9084 x, and then this one you got to bring it to that side as well, or you can just think of it as, you know, this has to be negative 1.6739 to cancel out, so you got to do negative 1.6739 there as well. So you end up just getting negative 1.6739. Okay, obviously this is all equal to 0 because there's nothing on this side right now. Now we're going to do our little quadratic formula. Okay, so x is equal to minus b. So x is equal to minus b. What is our b value? 1.9084. Okay, so 1.9084 plus or minus the radical. So within the radical, okay, so minus b plus or minus radical, b squared. What is b squared? It is 1.9084 squared minus 4a, right? A is 0.48. C is negative 1.6739 all over 2a. Okay, when I mean all over, literally mean all over. Okay, so this whole thing is over 2a. So 2 times 0.48. There we have it. So now we're just going to be putting them, and we'll first deal with whatever's in the radical first. Okay, so we're just going to chop this down one by one. So within this radical, try it on your own, you should be getting 3.6419. Okay, so 3.6419, and then this one over here, you end up getting 3.2138 or 9. Okay, in there I end up getting 6.8557. And then this is all going to be over our 2a. 2a would just be 2 times 0.48. You end up getting 0.96. There we have it. Let's keep working this way down. Our radical, so you're just going to square our 6.855, getting 2.6183. All divided by our 0.96. Now, if it's plus or minus, we're going to try and end up using both. Let's start it with the positive side. So you get negative 1.9084. You add it with 2.6183. And then you're going to divide it by 0.96. I end up getting 0.7395. 0.7395. Okay, so this here would be our positive value. For our negative value, you end up getting negative 1.9084. You minus 2.6183 and divided by 0.96. I end up getting negative 4.715. Negative 4.715. Obviously, this can be problematic. Obviously, this here is the incorrect answer. We got to be using this one, okay? Now, it's not always going to be that simple where one is going to be negative, so we're not going to use that one. It's pretty obvious we can't use a negative value. However, there is a possibility that you are going to run into a question where both of these are going to be positive, okay? Well, which one are you going to be using, okay? The answer is going to be as long as that value does not exceed the initial reactant concentration, because obviously it can exceed the initial concentration. That doesn't make sense, right? So if you have a value that exceeds this one or exceeds this one, right, obviously that number is too big, it's too large, that can't be the answer. So obviously the smaller value is going to be the correct one. Okay, in this case, this is just negative, so it's quite simple to rule that out. So let's use this one over here, okay? So let's bring this over. This is going to be our x value. We're going to be using that and putting that into our ER equilibrium row over here. So we're going to be first looking for a concentration of CO, okay? So for CO, it's going to be 1.45 minus our x value. What do you end up getting? You get 1.45 minus 0.7395. It is 0.711, okay? So 0.711 moles per liter, okay? So what do we end up having next? We have H2O, and our H2O is going to be 2.22 minus that value. What do you end up getting? Getting 1.48 moles per liter. Next, we're going to be dealing with H2. That should be simple. It's only going to be an x value. Same with our CO2. Okay, so those are going to be the same. So I'll just put here as well CO2. So our H2O and our CO2, both of them are going to be 0.7395 moles per liter. Same thing here, 0.7395. Oops, running out of space here. 0.7395 moles per liter. This is your answer. All right, these are 2 green questions of the day. This is going to be the first one. This here is going to be the second one. Please give this a try on your own. Please pause the video, and I'll be giving you the answers shortly. This is the answer to the first question. This here is the answer to the second question.